Good afternoon. We are now showing the corollaries of Carnot theorem. Corollaries of Carnot theorem. Okay. Now one corollary says that the efficiencies of all the reversible heat engines working between the same pair of high temperature source and low temperature sink are same. So what does it say? All the reversible heat engines working between the same pair of high temperature source and low temperature sink will have same efficiency. This corollary also we will prove by the method of negation. So in order to do that, let us take one high temperature source at temperature T1 and another low temperature sink at temperature T2. Between these we make one heat engine 1 work and heat engine 2 work between the same temperature source and sink, right? Now let us say eta 1 is greater than eta 2, say. So this engine is more efficient. Let us say this is taking Q1 amount of heat from T1 and delivering Q2 amount of heat to the low temperature sink and develops W amount of work. And the other heat engine which is less efficient, let it take Q1 amount of heat from the high temperature source and develop less amount of work because it is less efficient, which is W dash, and deliver Q2 dashed amount of heat to the low temperature sinks. Obviously it is by your assumption W dashed will be less than W, so your Q2 dashed will be more than Q2. Okay. The next moment what we do, since both the heat engines are reversible, any of them can be reversed or both can be reversed. So what I do, I reverse this heat engine. Okay. And if I do that, all the quantities will remain unaltered. So for this heat engine, everything is same. It is taking Q1 amount of heat from this high temperature source and developing W amount of work and delivering Q2 amount of heat to the low temperature sink. And this heat engine, the other heat engine, this is heat engine 1, this is heat engine 2. Here we have reversed the heat engine. So let us say Q1 amount of heat is going to the high temperature source and Q2 dashed amount of heat is moving from low temperature sink into the heat engine, and in order to do that it has to be fed W dashed amount of work. This W dashed is less than W, so I can get this W dashed from W amount of work. So the next moment what I do, I combine these two heat engines together and devise a single device. So what it is doing, the single device is working between the temperatures T1 and T2. So this is the single device. One part of this device is taking Q1 amount of heat and the other part is giving back Q1 amount of heat to the high temperature source. So the net heat interaction is 0. Q is equal to 0. But what is the interaction of this single device with the low temperature sink? It is taking Q2 amount of heat, Q2 dashed amount of heat, and giving back Q2 amount of heat. Q2 dashed is more than Q2, so the net heat taken from this low temperature sink is Q2 dashed minus Q2, and what it is delivering? See, this part is developing W amount of work, and this part is absorbing W dashed amount of work. So the net work delivered is W minus W dashed. Is that clear? What is W? W is nothing but Q1 minus Q2. And what is W dashed? It is equal to Q1 minus Q2 dashed. So what is W minus W dashed? So it is nothing but equal to this minus this is equal to Q2 dashed minus Q2. Is it okay? So what is happening in effect? That we have been able to devise a thermodynamic device. We have been able to invent a thermodynamic device which is taking Q2 dashed minus Q2 amount of heat from a single reservoir. Remember, with this reservoir the interaction is 0, and converting this entire amount of heat into work. So is it possible? No. Why no? Because this is a violation of the second law of thermodynamics. And which statement? The Kelvin-Planck statement. So our assumption that eta 1 is greater than eta 2 is not valid. In the same manner, you can prove eta 2 greater than eta 1 is not valid. In the same manner, you can prove. So what is the possibility? Possibility is that eta 1 must be equal to eta 2. Okay. And the other corollaries of Carnot theorem says that the efficiency of a reversible heat engine, it depends only on the temperature of the high temperature source and low temperature sink, and doesn't depend on the working substance of the heat engine which is used for the cycle, and not also on the quantity. This has got a very important bearing in second law, in thermodynamics. So with the help of this we will prove later the thermodynamic temperature scale. Thank you.